Hello, so in this video we're going to start talking about this thing called a power series. Now you may think, well, power series, why is that important to ODEs? Well, the whole point is that now if we start talking about power series, it allows us to talk about loads of different types of functions. So for example, up to now, just recently we've been talking about second order linear differential equations. So in other words, things that look like this, okay, y dash plus by, and that's equal to some kind of function on the right hand side, say for example. So we've been looking at something like that. Okay, and so far we've been looking at the case where these coefficients here are constants. They're just numbers, okay? And we've looked at various methods to kind of deal with them. So, for example, methods of undetermined coefficients. Okay, but now what we need to do in order to start talking about the case when these aren't constants. So, for example, they could be, say for example, this could be, I don't know, could be like sine t, and this one could be like e to the t, I don't know. So it's basically coefficients which vary according to their values of t which you put in. So they're not just a single value suddenly, they're not just like 3 or 5 or 7. They're suddenly values that can vary, so they're variable coefficients, okay? Well, in order to start talking about these cases, the second order differential equations involving variable coefficients, we need to start talking about power series, okay? But actually power series is very applicable in other areas as well, as we'll come on to talk about, okay? So first things first, what is a power series? Well, let's break it down, okay? Let's start talking about what a series actually is. So a series, okay, say for example if you have a list of numbers with some connection between them, then we call that a sequence, okay? So say for example we have 2, 4, 8, 16, 32, 64, okay? This is what would be known as a sequence, okay? Because the reason why this is a sequence and not just a list is because a sequence has to have a common connection between the variables. So in this case, the common connection is we multiply by 2 to get to the next term, okay? So it's got, it's a factor of 2, I suppose. Okay, so this would be called a sequence. Well, in order to turn this into a series, so we can carry on going, in order to turn this into a series, we just change these commas for pluses. Okay, so we just add the terms together, and that makes it into a series. Okay, so there we go. So we go plus. So that now is a series. Okay, so a series is just a sequence with pluses in between, just adding all the terms together. Okay, so that's what a series is. Now let's talk about what power actually means. Well, power, okay, if you have x raised to the power of something, that would be known as a power. The power would be the n. Okay, so if it's a power series, basically a power series is just writing. It's just a sequence. Well, let's talk about a power sequence, I suppose, first of all. So let's say, for example, we have x to the power 0. We start with x to the power 0, and the idea is with each term we just increase the power by 1. Okay, so we get x to the power 1, x to the power 2, x to the power 3, x to the power 4, and so on and so on and so on, all the way up to sort of x to the power of n and beyond. Okay, but of course the point with a power series, we could also have coefficients in front of them. So we could have, say for example, a0, okay, a1, a2. These are just numbers, by the way, and I'm just denoting them like this. So this could be like 3, this could be 4, this could be 5. But the reason why I'm writing them like this is because I'm just saying they're coefficients, and in general we're going to have n different lots of them. So rather than writing like a, b, c, D, E, whatever, we could have sort of more than 26 of them, and of course we've only got 26 letters, so we're going to fairly obviously run out of letters, which is why I'm using this subscript notation here. Okay, so I'm starting with, I'm saying this is a coefficient which corresponds to x to the power 0, which is what this subscript means, and this one is a coefficient associated with x to the power of 1, which is what this 1 means, okay, coefficient with x to the power 2, so this is what this 2 means, okay, so this is now a3, a4, okay, and so on and so on and so on. Okay, well the idea is now, so that would be a power sequence. A power series, we just change these for pluses. Just change these for pluses. So here we go. So go plus, plus, and plus. Now we can do a little bit of simplification. Okay, what is x to the power 0? Anything to the power 0 is always going to be 1. So it's just going to be 1 times a0. So therefore that's just going to be a0. Okay, then a1 times x to the power 1. Well, x to the power 1 we just write as x. Okay, so this would now be a power series. Okay, and basically the idea is that we can write pretty much any what's known as analytic function like this, okay, like this form, okay. In actual fact, we can condense this form into something which looks a lot neater, okay, and it's using summation notation. So a sum, okay, so it would be the sum, okay, of our coefficient so these are our coefficients, okay, little subscript of n, let's put little subscript of n here, times x to the power of n, times x to the power of n. Okay, so this thing is the same as this thing. So I'm just trying to write it out again. Okay, and going from n equals, well, what does our, our subscript is now our n, okay, and our power as well. So this is like, we start at a0, so we start when n equals 0, okay, and we can keep going. We can keep going all the way up to infinity. Okay, so this is how we would write this big, long series here in one neat, compact form. Okay, and that's basically the idea here. That's the idea here. So it's the summation from n equals 0 to infinity of an times x to the power of n. Okay, and the idea is that basically we can write any analytic function in this form. Okay, so we can write it as a power series. And that's quite useful, as you'll come on to see. Okay, so that's all a power series basically is. Now, at this point, you may be asking yourself the question, well, okay, I can kind of see how this would correspond to, say, like a polynomial. So what's a polynomial? Well, say, for example, if you have 3x squared plus 4x plus 2, that would be a polynomial, okay? I've just written, this is exactly the same power series as this, okay, expanded up to x squared. So it's exactly like that, just with sort of coefficients. I've just written it around the other way. We normally write it with the highest power first when we've got a finite number of terms, okay? So this would be here. So in other words, I could, if I carried on going, I could keep expanding this. Okay, so I could go plus x to the 4, but it would just be 0. So every term before that, or every term after that, depending which way you want to look at it. So every higher power, if you like, will just have a coefficient of 0. So this is still a power series. This is still a power series. So quadratic is still a power series with infinite amount of terms. It's just that it's just that all the terms above, say this oh sorry, that should be a 3, shouldn't it? Every term above the power 2 will just go to 0. So every coefficient above the power 2 will just go to 0. Okay, so hopefully that makes a bit of sense. So basically, a polynomial is just a power series. That's fine. But you may be saying, well, okay, but what about something like cos x, or something like e to the x? Right, or something like sine x, or something like this. You say, well, hang on a minute, that's not written as a power series. That is not written as a power series. That's not written in ascending powers of x. Well, actually, we'll see. Sort of, I don't know whether you've watched my video on Taylor series, but you can actually write these things as a power series using something called the Taylor series expansion. Okay, and the Taylor series expansion goes like this. So in other words, the Taylor series expansion is the summation from n equals 0 to infinity of the nth derivative. Okay, and we evaluate the Taylor series around some point. That's the whole point of the Taylor series. With the power series, we kind of just evaluate it. With the Taylor series, we have to evaluate it around some point. So in other words, we've got a function and we evaluate it around some point. And if you watch my video on Taylor series, that will all become clear. So let's call our point x0. So it could be 2, it could be 0, it could be 3. So x, it's just some point, and we're just going to call it x0. Okay, over n factorial. So that's, if you like, I always think that's like the coefficients. Okay, it's the coefficients sorted with. Okay, and then we just times it by x minus x0 to the power of n. Okay, and if you actually expand this out, it will end up looking something like a power series. Okay, let me just expand the first few terms. So let's start with n equals 0. We end up with f of 0. So the 0th derivative is just the function itself. Okay, evaluated at x0 over 0 factorial. 0 factorial is just 1. Okay, so that's just f of x0 over 1. Okay, times by x minus x naught to the power 0. Well, it's anything raised to the power 0 is just 1. So therefore, the first term is just going to be f of x naught. Okay, then we expand the second term. So we plus the first derivative, evaluated at x0 over 1 factorial, so that's just going to be 1, okay, times by x minus x naught to the power of 1, so that's just going to be x minus x naught. Let's just keep going for a little bit. So let's expand up to the third, I think. So the second derivative, evaluated at x0 over 2 factorial, well, 2 factorial is just going to be 1, okay, times by x minus x naught squared. Okay, let's just expand up to the third one. We can keep going in infinite number of terms, but let's just expand up to the third one. So third derivative of x naught over 3 factorial, which of course is just 6, okay, times by x minus x naught to the power of 3. And of course, this is something, the derivative evaluated at some point is something that we can actually evaluate. So in other words, we'll get a number. Okay, so in other words, if I just make this a little bit smaller, You know, this will just be some numbers. This is just going to be some constant. This is going to be some number constant. Going to be some number constant, and this is just going to be some number. So in other words, this will end up looking like a power series. This will end up looking like a power series. Okay. So in other words, what we can do is we can write any well-behaved analytic function like a power series. Okay. So that is all a power series basically is. And of course, a power series will have something called a radius of convergence. So the idea behind a radius of convergence, we'll come on to this a little bit further, perhaps in another video actually, I won't talk about it too much now. But a radius of convergence is basically the point where a function will converge. So basically if you expand it beyond that region, so say for example if you've got, you know, expanding a function, it goes like this, say for example, so this is our function, around a point x naught, so basically with each extra term of the Taylor series which you're adding, you're basically adding more. You're basically evaluating the function over a wider and wider interval. Okay, wider interval. Okay, well the idea is with the radius of convergence is that it's only convergence. So in other words, the function only converges to that value x naught for a particular radius. And that radius is what's known as rho radius. It's the Greek letter r. Okay, so for some radius, that would be the radius of convergence. So in other words, the function evaluated around that distance there will be convergent to x naught. Okay, but if we carry on expanding the function beyond that point, then basically it will diverge. So it will go off to infinity. Okay, and that's just basically what's known as the radius of convergence. So nice and simple.